So we're going to be going over how to compute one-sided limits algebraically. Now to get us started, we're going to do a real quick review on the different ways to express infinity and infinitesimals. Okay, so let's start with infinity. We have positive and negative infinity. So positive infinity can also be written as 1 divided by a very small positive number. And you should also recall that negative infinity can be written as can be written as 1 over a very small negative number. Okay, so 0 from the right um, is expressed as 0 with this positive exponent, and then 0 from the left, 0 with this negative exponent here. So that's for infinity, and then we have the infinitesimals. So for the infinitesimals, we have 0 from the right. So you think about an extremely small positive number. If you have an extremely small positive number, you can also write that as 1 over infinity, an extremely small positive number. And an extremely small negative number can be written as 1 over negative infinity, or negative 1 over infinity. They basically mean the same thing. Okay? Now let's take a look at some examples. The task is to evaluate the limit. So let's say we want to find the limit as x approaches pi over 2 from the left of negative 2 secant x. So let's say you want to find that limit. So what we're going to do is we're going to substitute. We're going to be plugging in pi over 2 into that x position right there. So let's go ahead and carry out the substitution. This becomes negative 2 secant of pi over 2 from the left. Okay. Alright, so we're going to evaluate negative 2 times secant pi over 2 from the left. Now, secant function is an asymptotic trig function, so we can use the reciprocal identity to express it into a function that's easier to graph. So we can write this as negative 2 over secant is the same thing as 1 over cosine. So negative 2 over cosine pi over 2 from the left. Okay? So you just have to remember that secant theta is 1 over cosine theta. And you also have to remember what your cosine function looks like, the positive and negative periods for your cosine function. You have a cup formation for your cosine function. Okay, so that's what we're going to be doing here. Now, what is cosine of pi over 2 from the left? To do this, we're going to draw our cosine function. It's like a cup, so we have pi over 2, pi, 3 pi over 2, and 2 pi. It oscillates between 1 and negative 1. So cosine will be starting from the maximum, so it goes like this through there, and then too far, like that. So that's basically what a cosine function looks like. Now we're approaching pi over 2, so this right here is pi over 2. Now remember, if you're descending towards a point, on the y-axis, what you're doing is you're approaching 0 from the positive or top direction. If you're descending. If you're ascending towards the x-axis, what you're doing is you're approaching 0 from the negative direction or the bottom direction. Okay? In this particular problem, what we're doing is we are approaching pi over 2 from the left. So if you're approaching pi over 2 from the left direction, what you're doing is you are descending. If you follow the trend of the line, if you're approaching pi over 2 from the left, you notice that you're descending downwards. So if you're descending downwards, that just helps you to see that cosine of pi over 2 from the left direction is a very small positive number. That's from the left. Okay? And then if you do the flip side, cosine of pi over 2 from the right, if you notice the trend here, you're ascending. If you're coming from the right, you're ascending. And in that case, from the right, you're going to have an extremely small negative number. Okay? So we're going to be making a substitution here. Cosine of pi over 2 from the left is a very small positive number. So when we carry out the substitution, we're going to have negative 2 divided by 0 from the right, a very small positive number. So we know what 0 from the right is, right? 0 from the right can also be written as 1 over infinity. 1 over infinity is the same thing as an extremely small positive number. Now what we're going to do next is we're going to drop, change, flip, okay? Multiply the top by the reciprocal of the bottom. Multiply it out. You have negative 2 times an extremely large number is going to give you an extremely large negative number. Negative infinity is your final result. Let's say that you're to evaluate the limit as x approaches negative 2 from the left of negative 1 divided by x squared minus 4. You want to do something like that. We're going to go ahead and substitute. We're going to have negative 1 divided by negative 2 from the left square minus 4. Okay? So you have to be really careful with the computation of negative 2 from the left square. It might not be what you think. When you square a directional number that's negative, what happens is that the sign and the direction changes. Okay? If you square negative 2 from the left, you're going to end up with positive 4 from the right. Let's illustrate that. Negative 2 from the left. What does that look like on the number line? So let's draw our number line to give us a visual. So this is negative 2, this is negative 1, and this is negative 3. We are approaching negative 2 from the left side. So this is negative 2 from the left. Okay? So what number is between negative 2 and negative 3 is negative 2.5, right? So when you're getting arbitrarily close to negative 2, what happens? From the left, this is negative 2.01. And then when you start getting really, really close, this right here is negative 2.0001. So if you get really, really close, negative 2 from the left is basically negative 2.00, infinite number of zeros, 0, 1. That's negative 2 from the left. So we're going to make that substitution. We're going to have negative 1 over, the number we are squaring is negative 2.00, an infinite number of zeros, 0, 1, quantity square, minus 4. Okay? Now what happens when you square 2.000001? Just to illustrate, to help you see the pattern here, let's play with some numbers. Let's do some computation here. So I'm going to start from 4.1. If I compute 4.1 square, 4.1 square, or let's do exactly what we have. So parenthesis negative 4.1. When you square that, you have 16.8. Actually, what I'm supposed to do is 2.1. So negative 2.1 square is 4.41. How about we do negative 2.01? So negative 2.01 square is 4.041. Let's do another one. Let's add in more zeros. So 2.001, enter. So you see the trend, more and more zeros are showing up. If you have an infinite number of zeros here, what's going to happen is you're going to have an infinite number of zeros, 0, 4, whatever. Okay? So what this helps us to see is that negative 2.001 squared is going to be negative 1 over 4.00, infinite number of zeros, 0, 1, minus 4. This number here is positive 4 from the right. Okay? Now we can use arithmetic to finish this off. You have 1 over, put the negative there, let's not forget that. 4.001 minus 4 is going to be 0.00, infinite number of zeros, 0, 1. This can be condensed into an infinitesimal, 0 from the right. Okay? And then 0 from the right, using the rules we talked about earlier, can be written as a fraction involving infinity, which is 1 over infinity. And then we're going to go ahead and drop change flip. Negative 1 times infinity over 1. When you multiply it out, your final answer is negative infinity. Okay? Let's say you're to evaluate the following limit. You're to evaluate the limit as x approaches 2 from the right. 2 from the left of a function where the function is the piecewise defined function defined as f of x equals x plus 3 when x is less than 2 and the square root of 2x minus 1 when x is greater than 2. So to find this limit, we're going to be substituting. So the question is, which one are we going to substitute it in? The first function or the second? Let's call the first function 1 and call the second function 2. To give ourselves a visual, what we're going to do is we're going to place the two functions on a number line, look at what direction we're approaching, and pick the correct function. Okay? So draw a number line. The break happens at 2. The first function is, let me color code this. Let's make the first function blue and the second function green. The first function is the region that's less than 2. So region 1 right here is the first function, and region 2 is the second function. Alright, so let me add on some additional details. So this is, for region 1 is x is less than 2, and for region 2, this is where x is greater than 2. When you're approaching 2 from region 1, this is the left side, so x is approaching 2 from the left. So this is approaching 2 from the left, and the other side, x is approaching 2 from the right. Okay? For this particular problem, we're focusing on approaching 2 from the left direction. Alright? So this problem is going to become the limit as x approaches 2 from the left of the function. We are now going to select the correct function. This is going to be the limit as x approaches 2 from the left of the function in region 1, which is x plus 3. Okay, so we now know which function to pick based on this split that we did over here. So we're going to be substituting this into this function. 2 from the left plus 3. 2 from the left plus 3. Let's think about it. 2 from the left, what is that? 2 from the left is 1.99. Infinite number of 9s, 9. When you add 3 to that, you're going to have 4.99. Infinite number of 9s, 9. So what number are you approaching here? The number that you're approaching is 5. Alright, so there goes your final result. Alright, so for question 4, what if you were to find the limit as x approaches 2 from the left of the absolute value of x minus 2 divided by x minus 2. Okay? So when you find the limits of absolute value functions, what you have to do is you got to replace the absolute value bracket with the expanded form. So this will be limit as x approaches 2 from the left of plus or minus quantity x minus 2 divided by x minus 2. This reveals the piecewise defined nature of this absolute value component. You're either going to take positive or negative. Okay? So we're confronted with the same situation that we came across in problem 3, where we have to pick one function. Alright? The break happens at 2. There is positive 2 and negative 2. Negative 2 is to the left, and positive 2 is to the right. So if we're approaching 2 from the right, we'll take the positive piece. If we're approaching 2 from the left, we're going to take the negative component. Okay? So since we're approaching 2 from the left, this is the scenario that we're looking at right here. Okay? So imagine this as interval 1 and interval 2. So we're coming from the left, we're going to take the negative component. Alright, so we're going to pick the negative one. So this is going to become the limit as x approaches 2 from the left of, you take the positive part, the negative part, sorry, negative x minus 2 divided by x minus 2. So that ambiguity with plus or minus is gone. We can now simply divide this out. And then this becomes the limit as x approaches 2 from the left of negative 1. You notice this is a constant function regardless of where x goes. This function will always be negative 1. So your final answer is going to be negative 1. So that's that.